welcome! And in this video, we're going to be solving logarithmic equations. Now, in the previous video, we talked about solving exponential equations. Well, in the previous two videos, we talked about that. Now we're moving on to logarithmic equations. And we're going to be covering quite a bit in this video, because there's a few different types of logarithmic equations you can encounter. Well, there's a lot, but we're going to be focusing on just the main few. One of which is if you have a single logarithmic expression in the equation, okay? These are actually some of the easier ones to do. If you have a single logarithmic equation or logarithmic expression in the equation, we're going to be covering those. In my opinion, the easiest one to do is actually when you have a logarithm on both sides. Well, actually a logarithm with the same base on both sides. We're going to be covering that, and then we're also going to be covering when there's multiple logarithms on one side. And this could be when there's a bunch of logarithms on one side and a number on the other side, or if we have multiple logarithms on both sides. We're going to be covering these three cases. But we're going to start with the first case, which would be an example such as this one. Now, in order to solve a logarithmic equation that only has a single logarithm in it, it's actually fairly similar to when we solved exponential equations that you could not use the one-to-one property. We wanted to isolate the exponential expression and then rewrite it in its inverse form. Well, that's actually kind of exactly what we're going to be doing here. We're going to be isolating the logarithmic expression and then rewriting it in its inverse form, which is an exponential. So that's exactly what we're going to be doing. So I want to isolate log base 4 of x minus 1. So the only thing that's on that side of the equation that's not part of that logarithm is that 3 over here. So I'm going to subtract 3 from each side to get log base 4 of x minus 1 is equal to 2. I subtract 3 from each side, and this is exactly what I get. Now we have the logarithm isolated. Now this is when we rewrite it in its inverse form. So we're going to be rewriting this in exponential form. Well, the base of the logarithm was 4. Well, guess what? The base of the exponential is going to be 4. So we're going to have 4 to the second power. The base is 4. The exponent is 2. 4 to the second power is equal to our argument of x minus 1. And from here, it's actually pretty easy. We just go ahead and solve. 4 to the second, well, that's 16. So we have 16 is equal to x minus 1. And now we add 1 to each side, and we get x is equal to 17. And this would end up being our final answer. Now, there is actually something that we need to address here. Remember, there are some specific restrictions with logarithms, and mainly regarding the argument of a logarithm. Remember, the argument of a logarithm must be a positive number. What that means is that in some cases, we're going to get what's called an extraneous solution. It's basically a fake solution. You do everything right, but the solution actually just doesn't work out. And it generally has to deal with domain restrictions of a particular type of function. And logarithms do have a restricted domain because that argument needs to be positive. So we always need to double check our answers. Basically, plug your answer back in and see if it makes any of the logarithm's arguments 0 or negative. If it does, get rid of that answer. It's a fake answer. It's what we call an extraneous solution. So I would actually double check this to be safe. And if I did that, I could go ahead and check 3 plus log base 4. Notice I'm going to the original equation. X minus 1, well, x was 17, so 17 minus 1 is equal to 5. I would simplify this a little bit. 3 plus log base 4. 17 minus 1 is 16, so it's going to become 16 is equal to 5. And now you can keep going. I'm actually going to stop right here. I know this is actually going to end up working. Log base 4 of 16 is 2, so I'm going to get 3 plus 2 is equal to 5. It checks out. But really what I'm really looking at here is that this argument is a positive 16. It checks out, so that answer actually checks out. That's going to be our final answer. That's just one extra step I highly recommend you do. We did talk about checking our answers with exponential equations. Here it's even more important because we can get fake solutions, so make sure that we watch out for that. Let's take a look at one more example of these types of equations. So let's take a look at this one. We have log base 3 of 4x plus 5 minus 2 is equal to 2. Well, once again, we have a single logarithmic expression here, so we're going to isolate it. So what I'm going to do is I'm going to add 2 to each side. So this is going to become log base 3 of 4x plus 5 is equal to 4. I would add 2 to each side to get 4. Now we have the logarithmic expression isolated. Now we can actually rewrite this in exponential form. The base of the logarithm was 3. The base of the exponential is going to be 3. So it's going to be 3, base of 3, exponent of 4, so 3 to the 4th is equal to 4x plus 5. And now we can go ahead and solve because this is actually linear. 3 to the 4th is 81. So 81 is equal to 4x plus 5. We're going to go ahead and subtract 5 from each side to get 76 is equal to 4x. Then we divide each side by 4 to get x is equal to 19. And that would end up being our final answer. And once again, you would want to double check just to make sure that 19 does not make the argument of the logarithm or any logarithm in the equation 0 or negative. So I'm going to plug that back in just to be safe. Log base 3 of 4 times 19 plus 5 minus 2 is equal to 2. Well, what this would end up becoming is log base 3 of, well, 4 times 19 is 76 plus 5. And actually, I'm going to stop right here. I know 76 plus 5 is going to be a positive number. It's going to be 81. So it actually checks out. So that would end up being our final answer. You can continue to double check. You can keep going and make sure that it actually works out. It just is going to work out in this particular case. And that's actually as simple as it is for solving a logarithmic equation when there's only one logarithm. Now I want to take a look at our second case, which is actually when you have a logarithm on both sides. And I really think we only need to cover one example of this because it's actually pretty straightforward. And it would be an equation such as this. Notice we have a single logarithm on both sides, and notice that the bases are the same. We have log base 3 on the left side, log base 3 on the right side. Now this is actually remarkably similar to when we solved exponential equations that had the same base. Remember, if you were able to have the same base of an exponential equation on each side, we used the one-to-one property where we set the exponents equal to one another. Well, guess what? Logarithms have their own one-to-one property. And it basically states that if we have a single logarithmic expression on one side of the equation and a single logarithmic expression on the other side of the equation, and both of those logarithms have the exact same base, we can then set the arguments equal to one another. So in this particular equation here, all I would have to do is set x squared plus 3 equal to 52. And that's because both of these logarithms have a base of 3. So that's all I would do, is I would say, hey, log base 3 equals log base 3. I can set the arguments equal to one another. So that's going to be x squared plus 3 is equal to 52. And now we go ahead and solve, just like we did back in Algebra 1 and back when we talked about solving quadratic equations. We can just use a square root here. So I'm going to subtract 3 from each side to get x squared is equal to 49. And then I would take the square root of each side. Now remember, when you take the square root of each side, that you have to do plus or minus. So this is going to be x equals plus or minus the square root of 49. And you can actually take the square root of 49 as plus or minus 7. Now remember, we need to double check our answer to see if it makes either of the logarithms 0 or negative. So I got to plug in 7 and negative 7 to see if it makes any of those negative. So if I did that, I get log base 3 of, let's do positive 7 first, 7 squared plus 3 is equal to log base 3 of, well, there's no x over here, so this is going to be 52. That's always going to be 52. That's kind of an easy one we can deal with. And notice this would end up becoming 49 plus 3 because 7 squared is 49. Okay, so that one checks out. 7 checks out. Let's check negative 7 now. So log base 3 of negative 7 squared plus 3 is equal to log base 3 of 52. Well, negative 7 squared is also 49. So we're once again going to get 49 plus 3. So both of these check out. Both of those would end up being our final answer. Now let's say hypothetically one of those logarithms ended up being like log base 3 of, say, negative 2. Whatever answer got you that, you would actually get rid of. That's what we call an extraneous solution. And these ones are actually kind of the easiest ones to cover. So we're actually going to move past this because the third case actually deals with both of these. Because in our third case, we can have multiple logarithms on one or both sides of the equation. Something like this. Notice here that we have logarithms on both sides, but we actually have multiple logarithms on one side of the equation. The left side of the equation has two logarithms. What do? Well, this is where our properties of logarithms are going to come into play. Remember all those properties. We had the product property, the quotient property, the power property, and how we were able to use those properties to expand a single logarithm or condense multiple logarithms. And that's exactly what we're going to be doing here. We are going to condense the logarithms on one side of the equation. Overall, if you have multiple logarithms on one side of the equation, the goal is to condense those down to a single logarithm. So the right-hand side of this equation is actually okay. There's only one logarithm on the right side of the equation. The left side of the equation, though, I see two logarithms there. I don't want that. I want one logarithm there. And notice both of them have, well, all of them in this particular case, have the same base. That's good. If they didn't have the same base, boy, are we talking about a much more complicated problem, and one that we're actually not going to be talking about. Now, because I have two logarithms on this left-hand side, and they're adding one another, I can actually use the product property there. Recall those properties that if you have two logarithms adding one another, you can condense those down to a single logarithm by multiplying their arguments. So what this is going to end up becoming is log base 9 of x times x plus 13. X times x plus 13. They are multiplying each other because the logarithms are adding one another. And that's going to be equal to log base 9 of 48. And now I'm going to clean up this left-hand side first. I'm going to distribute that x. So it's going to become log base 9 of x squared plus 13x. I'm just going to go ahead and distribute that there. And now look what I got. I have a single logarithm on both sides of the equation. That's exactly when we used the one-to-one property, just in the very last problem. Remember our one-to-one property. If we have a single log on each side of the equation and both have the same base, that means the arguments must be equal. So now what I can do is I can set these arguments equal to one another. X squared plus 13x is equal to 48. And I can solve this. And oh man, what are we going to have to do? We're going to have to factor. Don't forget about solving by factoring. Man, is this going to come back in a big way. So I got to get everything on one side of the equation. X squared plus 13x minus 48 is equal to 0. And if you don't recall solving by factoring or factoring in general, make sure you go back and watch those videos or get some help because that is so crucial to pretty much everything we're going to be doing from this point on. So now I can go ahead and factor this. And this would actually factor to x plus 16 and x minus 3. And that's equal to 0, which gets me two solutions of negative 16 and positive 3. Now remember, we need to check to see if these solutions actually work. We need to see if we have what's called an extraneous solution. Well, if I plug in negative 16 for x, if I plug negative 16 in for x, I would get log base 9 of negative 16 plus log base 9 of negative 16 plus 13 is equal to log base 9 of 48. Now, notice not only are one of these logarithms going to become negative, or the argument becomes negative, actually two of them. This argument's negative, and this argument would end up being negative as well. We can't have that. The definition of a logarithm states that the argument must be a positive non-zero number. So what that means is that negative 16 is actually not a solution. It's what we call an extraneous solution. My apologies for the crappy handwriting there. It's what we call an extraneous solution. It's actually fake. We would not list that as an answer. However, if we check positive 3, if I plug in positive 3, I'm going to plug it back in. Log base 9 of x, well, x we found is 3, plus log base 9 of x plus 13, which we got is 3, is equal to log base 9 of 48. Notice none of these logarithms arguments are negative in any sort of way or will become 0 or negative. So that actually checks out. So 3 would actually be the only solution here. So that's an example when we have to be especially careful, okay? Now, If, say, both of them didn't work, we would actually have a no solution, okay? Now, that doesn't mean that both won't work or only one will work. You can get a bunch of different answers for these types of equations, or you can get no answers. It's all dependent on that particular problem. There's no like quick way to know. There's no tip or trick I can tell you. Just go in there, do the grunt work, and determine for yourself. Now I want to cover one more example, and it's going to be a little bit different from this one. So let's take a look at this one. So we have two logarithms on the left-hand side, and we don't have any logarithms on the right-hand side. So what we can do is we can condense the logarithms on the left-hand side to a single logarithm, and that's exactly what we want to do. Now notice, these two logarithms, they have the same base of 4, and they are subtracting one another. Well, that's the quotient property. When you have two logarithms subtracting one another, that means their arguments are dividing. So I can condense this down to log base 4 of x plus 6 over x is equal to 2. And now notice this is actually very similar to our first two examples. We have a single logarithm now. So now we go ahead and we can rewrite this in exponential form. The basis for the logarithm, the basis for the exponential. And the exponent is going to be 2, so 4 squared is equal to x plus 6 over x. And now we go ahead and solve. Let me move this up here. So this is going to become 16 is equal to x plus 6 over x. Now notice I have an x in my denominator. I don't necessarily like that, so I'm actually going to multiply each side by x to get 16x is equal to x plus 6. And now I can go ahead and solve a little bit easier. I can subtract x from each side to get 15x is equal to 6. Now I can divide by 15 to get x is equal to 6 over 15. And I'm actually going to reduce that. That is a fraction that you can reduce. That reduces to 2/5. So we get x is equal to 2/5. And once again, you would want to double check this as an answer. Plug it back in. I'm going to tell you right now, it ends up working. So this would end up being our final answer. And that is solving logarithmic equations. Now I'm going to go ahead and make a follow-up video just with some straight examples, with some extra practice. I think a lot of people can benefit from this, okay? But this really is solving logarithmic equations. So I hope this video was helpful. If there's any questions, please feel free to let me know. Otherwise, I look forward to seeing you guys in the next video.